Well, hello, students. It's Mr. Rich. It is Sunday night Q&A. Welcome to another night of math problems. I do have problems that have come in from some students, and I'm going to work as many of these as I can. If you are watching live and you're one of my students, you have my email address. You know what it is. You can send me a copy of a homework problem. I'd be happy to work it for you. If you are watching live, but you're not one of my students, you could submit it over in the comment section. I'll keep my eye open for any comments that come in. Also, I'll keep my eye on my inbox in case anybody sends in some during the live session here. So I'll share my screen here in just a second, but just first let me introduce myself. If you don't know who I am Mr. Rich. I'm a math tutor here in Jacksonville, Florida. I used to teach at Stanton College Prep here in Jacksonville, Florida. AP Calc and AP Stats is what I taught primarily. And now I coach students in all levels of math. And we have a team of tutors that helps really anywhere from middle school math all the way up through AP Calc and AP Stats and even into some college math classes. So if there's anything I can do to help you, I'll give you my phone number and my email address here at the end, and you certainly could reach out to me. All right, so let's get started. I am going to go ahead and share my screen, and we will get started working some math problems. Here, and there I am down in the lower right hand corner. I think we got it. So the first question that came into me was a geometry problem involving triangles. I know in our area, a lot of the students that are in geometry or geometry honors are working with triangles. And so this was simply asking us about finding the measurement of all of these angles in this particular picture, where it tells us that the triangle ABC is an isosceles triangle. So that bigger outer triangle here that we're looking at is isosceles. And therefore, we can make the assumption that AB and BC are of the same length, in which case, then angles A and angle C would be congruent angles. So it looks like what we're going to do is start off by making an equation. 9x minus 47 for angle C has to be equal to 4x plus 3. We'll subtract 4x on both sides, and we'll add 47 on both sides, and that gives us x is equal to 10, which allows us then to find the measurement of angles A and C. If x is 10, you can see that that's going to make angle 1, which is angle A 43-degree angle. And then angle 9 is 43. And then you're kind of off and running at that point. But let's see where we need to go from here, because it says that DBE is equilateral. So this inner triangle right here, DBE, being equilateral means that angles 4, these are degree measurements, so we want to put those on there. And angle 5 and angle 6 are all 60-degree angles. So that helps quite a bit fill in the blanks that we need. Because if those 3 are all 60, then that would mean that angle 3 is 120, because that's a linear pair. And linear pairs have to add to 180. So we get this right here. Angle 3 would be 120. Angle 8 would be 120. And then the only ones that we don't know are 2 and 7. And what we can do is work with the inner triangle right here. And cleaning this out here, we knew that this was 43 degrees, that this was, this was 120, right? So when you add 120 and 43, that gives you 163, leaving me 180 minus 163, or 17 degrees for both angles 2 and 7. So that would be our last two angles, 17 degrees. All right, no other questions have come in, but let's keep going. The next one that I wanted to go over was a problem that a student had asked me from AP Pre-Calc. This, I believe, was a summative question. It says that the exponential function f is defined by f of x equals a times b raised to the x, where a and b are constants. If f of 2 is 36, and this was where a lot of the confusion was, if f of x plus 1 over f of x is 3 for all values of x, which of the following is the expression for f of x? So they're giving us the format for the equation. They're giving us one ordered pair, which is 2 comma 36. And then they're giving us that piece of information. So you can't really make sense of that unless you maybe rewrite that. If you haven't seen that before, that would tell you that f of x plus 1 would be equal to 3 times f of x if you just multiply both sides by f of x. Now, what does that tell you, right? This tells you that if you want to get the y value for the next x value after this one, you have to multiply this by 3. In other words, let's do it this way. I hadn't thought of this when I was talking about this to the student. But if I know that f of 2 is 36, let's let x be 2 in this equation. That would mean that this would be f of 3, 2 plus 1. That would be 3 times f of 2. Now, we know that f of 2 is 36. So that tells me that f of 3 is 3 times 36, which is 108. That means that that's telling me that when x is 3, the y is 108. So when we incremented the x by 1 from 2 to 3, we multiplied the output by 3. That's what this is telling you right here. So this is just a way of saying that the base of the exponential is going to be 3. It's what we call the common ratio when we were talking about geometric sequences. So we really know that f of x is equal to a times 3 raised to the x power, because of that 3 being that value right there. Then what we could do is we need to find out what a is. Okay. And that would just require us to maybe divide by 3 twice. However, let's just go ahead and plug this point in. 36 is equal to a times 3 to the second power. 3 to the second power is 9, so a is 36 over 9. It's 4. So we know that b is going to be our answer right there. All right, so hopefully that is of interest to you AP Pre-Calc students. You might have seen that one on your test. Let's go to the next question. Keeping my eye peeled here for any problems coming in. I don't see any. And we're looking at the comments. I don't see any comments coming in. All right, let's keep going. The next question was an AP Calc question that came in. This said, find the critical values, relative extremes, and intervals where the function is increasing or decreasing. I have worked this problem with several students this week as they're getting started in Unit 5 of AP Calc. And what we're finding in Unit 5 is how to use derivatives to find relative extreme values for a function. That is where functions change from increasing to decreasing or vice versa. And so what we are going to do is we're going to find critical values by taking the derivative of the function. Now, one of the things that I do emphasize to students who are starting in Unit 5 finding critical values is you have to know what critical values are. that critical values are values for a function that would make its derivative equal to 0 or make it undefined, so long as that x value is in the domain of the function. So what we're going to do here is we're going to take the derivative f prime of x. Now, we will rewrite this as x to the 1/3 power minus 1. So we're going to transition this radical into a fractional exponent. Now I can use my power rule of exponents when I take the derivative. That's going to be 1/3 times x raised to the 1/3 minus 1, which would be 2/3, and the derivative of the -1 is 0. I'm going to rewrite this by using the negative exponent rule and push that x to the -2/3 into the denominator, and I'll write it like this. Now, when you're dealing with derivatives that are rational functions like we have here, rational functions have a top and a bottom. The derivative will be equal to 0 when the numerator is 0. Fractions in general are 0 when the top of the function or the top of the fraction is equal to 0. Well, there's no values of x that will make this derivative 0 because there's no x in the numerator. However, there is a value of x that will make the denominator equal to 0. And that would make the solution to setting the denominator equal to 0 would give me a value of x that would make the first derivative undefined. And when you solve that for x, the answer is x equals 0. Now, I do need to check and make sure that that value of x is in the domain of the original function that we started with. And it is in the domain, right? The cube root of x, 0, is in the domain because we can take the cube root of 0. It's 0. So this is a critical value for this particular function. So we will do what we would call as a critical value number line analysis. We will plot the critical value that we found, 0. If I had found multiple critical values, I would be plotting all of them on this x-axis. And then what I'm going to do is I'm going to pick a value of x that would be to the left of 0. I'll use a -1. I will choose a value to the right of 0, which would be x equals +1. And then what I want to do is find out what the sign is for f prime of x when x takes on these two test points, -1 and 1. And when I plug in up here, my derivative, when I plug in -1, that's going to give me a positive value. Now, why will it be a positive value? I had several students who looked at this and told me they thought it would be negative. But when you stick a -1 in, or a negative anything into this function for x, what you get is -1 raised to the 2/3 power. That's going to turn out to be a positive value because the cube root of -1 would certainly be -1, but then you are squaring it because of that numerator of 2. So it's going to turn it positive whenever you square any number, negative or positive. It will be a positive number. So both of these test points, when I plug them into the derivative, will give me a derivative that's positive. Notice we don't care about whether it's what the numeric value is, just the sign, whether it's positive or negative. And why do we want to know that? Because this tells me what the behavior is of f of x. It tells me that it was increasing, right, over this entire interval from -infinity to 0, because the derivative is positive. Over here, the derivative is positive, so it's increasing. So as it turns out, although this is a critical value for f of x, it's not a relative min or max, because the definition of a relative extreme is where the function changes direction. It would have to change from increasing to decreasing, in case it'd be a relative max, or decreasing to increasing, in which case it would become a relative minimum value. So it has neither. So there are no relative extremes for f of x. If this question did ask me about where is this function increasing or decreasing, this function, I could say, is increasing over its entire domain, negative infinity to infinity, like that. And yeah, so that's one thing that we can say. Now, it is true that if you go back to pre-calc and even algebra 2, you should have been able to make a sketch of what that function would look like, because that is really just a transformation of one of the parent functions that you're supposed to know what it looks like. And here's what I mean. What does the cube root of x look like? All right, let's just take a quick look back in algebra 2. Cube root of x functions take on this characteristic shape. They have what we called a point of inflection at the origin, and then they went like this, and then they came out like this. And that's a bad picture there coming in. I'm going to redraw that. So this thing comes in and goes vertical right there, and then comes down and comes out this way. That's just a rough sketch of the behavior of the cube root of x. Now, the function we were dealing with was just the cube root of x minus 1, meaning that you shifted the whole thing down by 1. So that point of inflection was really moved down here. And so it was doing something like this. Okay, so no surprise that we got the result that we did in our analysis, that the function is increasing to the left of 0, and then again increasing to the right, because you can see that in the graph right there. Okay, and no relative extreme that exists there for that function. You know, just on a side note, I was talking with a few calc students this week, and I was explaining to them, you know, that now that you're in calculus, you have the tools to find locations of where functions have relative extremes, right? Relative maxes and relative mins. And you haven't really known that. You haven't had that ability in your prior algebra classes. Nobody ever asked you, hey, find where this function reaches a maximum value. With one exception, though. I told them that ever since algebra 1, you've known how to find critical values of quadratics. And so I asked students, I said, if you have a quadratic that's written in standard form, they would have never asked it this way in algebra 1 or 2. They would have never said, what are the critical values of this quadratic? They would have said, what is the axis of symmetry? And the axis of symmetry is the x coordinate of the vertex. If you have a parabola that has a vertex here that opens up like this, you would agree that this right here would have to be a critical value, because that is a relative min value. But there was an equation that we gave you for that. To find that x coordinate of the vertex, we called it the axis of symmetry. It was the equation negative b over 2 times a. Now, where does that come from? Where did that come from? It came from calculus. Because if I gave you now this equation for a quadratic, and I told you to find its derivative, using your power rule, you tell me it's 2ax plus b. And then if I said find the critical values of this quadratic, you would take the derivative and set it equal to 0. And if you solve that for x, you would subtract b and then divide by 2a. You would get x is equal to negative b over 2a. That's the critical value for the parabola when it's written in standard form. Okay. All right, I've got a few more questions. Let me take a quick check here and see if any more problems have come in. It does not look like it. All right. Let me make one quick commercial here for you. Notice I do have an AP pre-calc group that I wanted you to be aware of. Now, this group meets Sunday nights at 9 o'clock right after this session here, and it's a small group. We've got less than 10 students in it, and what we do is every Sunday night we'll do a 1 hour where I'll talk about the lessons that we had for that week and what's coming up. Right now we're in Unit 2, and we're in logarithms, right? So we're at the last part of Unit 2, where we deal with logarithms and log modeling and semi-log plots. So we'll be doing that probably for the rest of the semester. We may get into Unit 3 right before the winter break, but we'll see. But if you are interested, you can drop me a note, and I'd be happy to give you more information about it. And in addition to the weekly live group session, I do give you access to my private online classroom on AP Pre-Calc that gives you some additional resources. Okay, so just wanted to mention that to you. All right, back to working a few more homework problems. And there we go. Okay, so I'll keep myself over here on the right side, unless we need to get into our calculator. The next homework problem that I had was Algebra 2. So I've had a few students ask me about trying to solve equations that kind of look like quadratics but are not quadratics. And I want to show you two different ways that you can handle this. So when you look at this problem, it does look like a quadratic, x to the fourth plus x squared minus 42. And you can factor it in the same way that you would factor a quadratic into the product of two binomials. And what you could do is say, gee, what would give me x to the fourth here in these two spots? That would come from x squared times x squared in my binomial. And that's going to work because when you were FOILing this out, if you're multiplying the two binomials, you'd need an x squared, and that's going to come from the outer and inner products of the two binomials. So now we can really do the same technique that we would use if this was a true quadratic with an x squared and an x right there. And let's go back. I lost my place here. There we go. So we could still ask the same question. If I should say, what two numbers multiplied would give me this negative 42? But when I add those same two numbers, I get a positive 1. And if you go through the different ways you could multiply integers to get negative 42, one of them would have to be a positive and one would have to be a negative. So it's either a 7 and a negative 6 or a negative 7 and a positive 6. Okay, you could do 14 and 3 as well. 14 and negative 3 or negative 14 positive 3. Those two numbers will give you negative 42. But these are the ones I want because they need to be 1 apart. And since I'm looking for a positive 1, I want the 7 to be positive and the x to be negative. So that when I do the FOILing on this, my outer product will be a positive 7x squared, and my inner product is a negative 6x squared, and those combine to give me the proper middle term of 1x squared. All right, so now that we have factored this, what do we do once we have successfully factored a trinomial into the product of two binomials and we have it set equal to 0? What we would do here is we would set each one of these equal to 0. So I'm going to set x squared minus 6 equals 0 and x squared plus 7 equals 0. To solve this one, I would add 6 on both sides. I would square root, and I get plus or minus the square root of 6. So I get two answers there, and those are two real answers. They are irrational answers, but they are real. Over here, though, when I subtract the 7 over, it's going to be x squared equals negative 7. And then I will square root both sides, but that's going to give me the square root, plus or minus, of a negative 7. That makes that an imaginary answer, or what we call a complex answer. So that's going to be rewritten as x is equal to plus or minus I times the square root of 7. So we get a total of 4 answers to the original equation, but 2 of them are real and 2 of them are imaginary or complex. Now, when I coach students, I always like to show them what things look like in a graphing context. What does this look like if I were to graph the function y equals x to the fourth plus x squared minus 42? So what I'm going to do here is pull up Desmos, and we are going to take a look at the graph. Let's spread this out just a tad, and then let's graph y equals x to the fourth plus x to the second minus 42. And that is the function. It looks like a quadratic, doesn't it? But it rises much faster. I'll spread this out a bit and maybe go from -3 to 3, -3 to 3. And then you get maybe a little bit better picture. But what we do see, if I'm going to find a solution to this, I would be looking for the x-intercepts. Now, I'll take just a quick moment here and discuss this, how I teach it to my SAT students that I'm prepping. Anytime that you are solving an equation in one variable, what I recommend that you do is you graph the left-hand side of the equation, which is what I've just done right here, and you graph the right-hand side, which is y equals 0. So you graph them as 2 separate functions. Now, I know that y equals 0 is the x-axis. So sure, the x-axis is going to light up here in green. It's the intersection of the graph on the left and the right that gives you the solutions, and it's just the x-coordinates. So you can see that we've got a positive 2.44949 and a negative of the same, and that's what square root of 6 is. Just to check, if you do the square root of 6, yeah, that's where those 2 x-intercepts come from. Those are our 2 real solutions. Notice, excuse me, that the imaginary solutions right here, those do not show up on the graph. They are not x-intercepts. So only the real ones show up. Okay, let's carry on. And the next one, and then we got some other pre-calc coming up as well. All right, solving this one. Well, the first thing that I notice is I want to factor out a greatest common factor, and I know that there's a common factor of 2 that we can pull out, and as well there's an x squared. So I can pull 2x squared out, leaving me x to the fourth minus 5x squared minus 24 equals 0. Now what I will do is go ahead and factor this in a like fashion from the prior one. I'm going to split this up into the product of 2 binomials. However, since that first term is an x to the fourth, I'm going to split that up as x squared. Now that's working because it goes x to the fourth x squared. If this was x to the fourth and then x or x to the third, then this is not going to work. There'd have to be some other way for us to factor it, like polynomial division or synthetic division. So, but what I can do is I can say, okay, what 2 numbers multiply to be -24, but they add to be -5, right? Since that's a -24, one's going to be positive, one's going to be negative. And if you go through the options here, 8 and 3 are what we're looking for. So I need a -8 and a +3. They multiply to be -24, and they combine the outer product and the inner product in the multiplication of these 2 binomials. Those 2 products will combine to be the middle term of -5x squared. And then what I will do, now that I have factored, I have to set each of the 3 factors equal to 0. Well, I'm not going to really set that equal to 0. I'm going to do the mental algebra that if I set 2x squared equal to 0, that gives me a solution of x equals 0. This one, if I set x squared plus 3 equals 0, I'm going to get 2 imaginary solutions because I'm going to get x squared equals -3, and therefore I would be square rooting both sides. That's going to be plus or minus I times the square root of 3. Over here, I would set the x squared minus 8 equal to 0. That's going to give me x squared equals 8. And then I could square root both sides. That's going to give me plus or minus 2 root 2 when I simplify the square root of 8. And those are my solutions there. Now, what does this mean when we take a look at how many solutions do we have here? Well, what we've got are really 5 different solutions. X equals 0 occurs twice because of this x squared, but I have an x equals 0, 2 imaginary solutions, and then 2 other real solutions over here. So I have a total of 3 real solutions, the x equals 0 and the plus or minus 2 root 2, and then here's the 2 imaginaries. So if you were to graph this, I'm going to make a prediction of what's going to happen. Let me just go over that for you Algebra 2 students. What we do know is we could make a very rough sketch of this function. We know that one of the x-intercepts is here at 0. Now, 2 root 2, let's see, square root of 2 is about 1.4, so times 2 is about 2.8. So it's going to come out here to 2 root 2. And back here at negative 2 root 2. Now, let's talk about the end behavior of this function. It is an even degree with a positive leading coefficient. So the end behaviors are up to the right and up to the left. So the function would be coming from the right side up here. It's going to cut through this x-intercept, turn to get to the other x-intercept, but because of the 0 at x equals 0 has what we call a multiplicity of 2 on the factor that created it, it will bounce or reflect off of the x-axis like this, in which case it's going to turn and then head up this way. So that is approximately what we should see. Now, we have no idea, I have no idea how low it's going to go here or how low it's going to go here. But what we can do is go ahead and graph it, and let's see what this would look like. Let me move my head out of the way up here, and then we will type this into Desmos just to see if these intercepts and the shape of this graph would match what we think it is. So we've got 2x to the 6th minus 10x to the 4th minus 48x to the 2nd power. Right? And then we'll spread this out to get a better look at it. And I'm going to change my scale here to go from about -4 to 4. And on this y scale, my goodness, let's go from -200 to 200. It didn't like my double negative there. Okay, there we go. All right, so that is what the function looks like. And what we said is not far off, at least in terms of just the general behavior of the function. You can see right there. And you can see how steep it is here. I mean, it looks like almost vertical lines right here, but that's because it's getting very, very steep because it's a 6-degree polynomial. But you can just see, the main point I wanted you to see is it is going to bounce here off of the x-axis right there. Okay, if you're just joining me, if you have any comments or questions or homework problems that you'd like me to work, you can post them in the comments section. If you're one of my students, you have my email address. You know what it is, and it starts with the word ask. And in the invite that you got for tonight, you will see the email address, and you can you still have some time to send me in a homework problem. I do have one more, which will be kind of our last work for tonight, unless I think I've got 2 more. I've got another calculus down there, but let's talk a little bit about logarithms. These are for the AP Pre-Calc students that are starting logarithms. If you are an Algebra 2 student, you'll be getting to logarithms probably in the spring, sometime around March or February, perhaps. But here, we are evaluating logarithm expressions without a calculator. These are all logs that could be expressed by knowing the properties of logarithms. And I'm going to explain logarithms like really we would explain them in AP Pre-Calc, right? Logarithms are inverse operations of exponential functions. So what does that mean, an inverse operation of an exponential? So what I mean is this. In order for me to show you how to evaluate these properly, I want you to understand something extremely important about logs and exponentials. That if I were to show you an equation, I'm going to insult your intelligence here for just a few minutes. You all know that 3x equals 27, that if I was to use algebra to solve for x, I want to use the inverse operation of multiplication. I want to get rid of this multiply by 3. And you know that the inverse operation of multiplication is division. So I'm going to divide both sides by 3 right here. And when I do that, I get x equals 9. So when I apply an inverse operation to a function, it gets rid of parts of the function that I don't want to be there on that side. And I can use and employ these inverse operations as long as I'm doing it to both sides of whatever equation I'm working on. As you know, subtraction is the inverse of addition and vice versa. And even when it comes to exponents, for example, if I have x to the 2/3 is equal to 16, and I want to solve that for x, well, the inverse operation would be a power of 3/2. X to the 2/3 to the 3/2 is just x to the 1 power, and this would be 64. Right? I would take the square root of 16, which is 4, and then I would cube it. 64 is the answer. So we have these things called inverse operations. Well, we have those for exponentials. Let me show you what I mean. If I say I have 5 to the x equals 25, now you probably would guess by inspection that that's got to be x equals 2. However, if I want to get rid of this base 5, we call that an exponentiation by 5. I'm going to use a logarithm of base 5. I'm going to take the logarithm base 5 of that 5 to the x, which is fine as long as I do the same operation on the other side. So what happens when I take log base 5 of 5 to the x? Those two inverse operations, in a sense, cancel each other out, leaving me just the exponent x. And so x is log base 5 of 25. All right. Now, and then you may say, well, okay, well, how am I supposed to know what that is? Well, that answer is going to be 2, but let me show you why it is 2. All right. So here's why. I'm going to show you how to get rid of a logarithm. Suppose you had log base 5 of 25 is equal to x, and you want to get rid of log base 5. You would do something called exponentiate. And when you take 5 to the log base 5 of 25, those two inverse operations cancel, and you're left with 25 equals 5 to the x power. So what we can do is we can use these logs and exponentiation as inverses. Let me show you how we're going to evaluate these. Oh, well, I think what I most want you to see as I was showing you these examples is that if I do have a match between the base of my logarithm and the base of the exponential that's inside the argument, they will cancel each other out. So my strategy is to rewrite this argument so that it matches the base here. So I'm going to call this log base 3 of 3 to the second power, because 9 is 3 to the second power. Those cancel. The answer is 2. This is 6 squared. Log base 6 of 6 to the second is an answer of 2. What's natural log? Well, that's log base e. I could rewrite this as log base e of e to the 0 power, because e to the 0 power would be this 1. That's 0. So anytime you're taking a logarithm of the number 1, the answer will always be 0. That's something to always keep in mind that you will use from time to time. All right. If I have a log that does not have a base on it, it's a log base 10. So this is log base 10. It's an invisible 10 of 10 to the first power. The answer there is going to be a 1. Okay, I have maybe just one more problem to work. I'm going to make one quick check to see if anybody has submitted any homework. I don't see. I do see one. Tyler has submitted one. So let's take a look here. I'm going to copy this over. This just came in from Tyler, it looks like. Thanks, Tyler, for sending that in. Let's paste it in there. Okay. Oh my goodness. It's a stats problem. I was looking at maybe some parabolas here, but let's see if we can make some sense out of this. So this says the name of the water hole comes from the small lake that lies between the tee where the ball is hit and the hole. Miguel has 2 approaches to hitting the ball from the tee, the short hit and the long hit. The short hit results in the ball landing before the lake. The values of X in the table are based on the short hit. The long hit, if successful, results in the ball traveling over the lake, landing on the other side. The 2 approaches are shown in the following diagram. All right. Now, they mentioned here, Tyler, a table. Is there a table that goes with this? Because it's talking about values of X. I feel like I've seen this problem before. I'm looking at parts C and D. Do you have any? Can you send me over the other parts maybe that I'm missing? All right, I'll hang tight here and keep my eyes peeled to see, because I don't. Well, I'll keep reading this. A potential issue with the long hit is the ball might land in the water, which is not a good outcome. Miguel thinks that if the long hit is successful, his expected value improves to 4.2. However, if the long hit fails and the ball lands in the water, his expected value would be worse and increases to 5.4. So part C says, suppose the probability of a successful long hit is 0.4. Which approach, the short hit and long hit, is better in terms of improving the expected value of the score? Justify your answer. Boy, I feel like I don't have enough information there. I don't see that he's back on here. All right, might have to come back to that one, Tyler. I don't see that we got everything that we need there. All right. Let me just show a few more of these. Evaluating logarithms. We could write this as log base 6 of 6 to the 1/2 power, right? Converting that into a fractional exponent lets me see that the answer to this is 1/2. Also, students, don't forget that you do have access to your TI-84, maybe for homework. It's on a lot of your summatives you won't. I understand that. But there is a command on the TI-84 called logbase. It's on the math command. If you scroll up from the bottom, you'll see the log base, and you can put your own base into the logarithm. So you could put 6. If you're doing this problem here, you could do log base 6 of the square root of 6, and you'll see that it'll return an answer of 0.5 right there. In Desmos, it does have an arbitrary base logarithm. What you have to do though is you have to use their keyboard, go into functions, and I believe it's at the very bottom down here. Yeah, right here. So you could put a no, wait, sorry, we're talking about logarithms. It's in the calculus section, if I remember right. So if you come down to the calculus part, yeah, so you can put in a log base 6 of square root 6, and it returns a value of 0.5. So you have that option in both the TI-84 and Desmos. Just wanted to show that to you. Okay. And then Tyler, if you do end up watching this again, email me directly, and I'll be happy to help you with that problem. Okay. All right. So I think we're going to cut it off there, students. If you are watching this live, then I appreciate you attending. If you're watching this by video on replay on YouTube, I will give you my my contact information here. Let's see if I can find it for you. And there you go. So down at the bottom there, you'll see my phone number, our website there, and then my email address where you can reach me. So if there's anything I can do to help you, whether it's one-on-one tutoring, if you're interested in our group tutoring, also I can give you information about that. And we do tutoring for all topics of math. So anything we can do to help you, let me know, and I'll be happy to talk to you. All right, everybody, I hope you have a great week. I am going to have this session next Sunday night, even though it is going to be the week before Thanksgiving. I know some of my students are going to be in class Monday and Tuesday next week before Thanksgiving, so I'll be here. So send me your homework questions. If you're my students, you have my email. Send me your questions throughout the week, and I'll hold on to them, and then we'll address them like I did tonight, all in one session. Okay, everybody, I will see you next week. Take care. And if I don't see you, have a great Thanksgiving.